Back on Earth, we waited breathlessly for the first images. Viking painted its picture in vertical strokes, line by line, until with enormous relief we saw the footpad securely planted in the Martian soil. This was the first image ever returned from the surface of Mars.
Welcome to Moonshot. I'm Christopher Lawson, and you've just been listening to Carl Sagan describe the very first images taken on a planet outside of our own, captured by NASA's Viking 1 lander shortly after it touched down on Mars in 1976. For thousands of years, humans have looked up into the night sky, gazing at distant stars and not-so-distant planets. One of these pinpoints of light is Mars, our next-door neighbour in the solar system. Until recently, we had no idea what this planet was really like, and that mystery-fueled imaginations of a planet filled with aliens and exotic landscapes.
Invaders from Mars, capturing humans at will for their own sinister purposes, turning them into diabolical instruments of destruction.
But in 1976, that changed.
Beyond the lander itself, we saw for the first time the landscape of the red planet. It didn't look like an alien world. There were rocks and sand dunes and gently rolling hills, as natural and familiar as any landscape on Earth. Forever after, Mars would be a place.
We now know a lot more about Mars than those early visions of the planet, with dozens of orbiters, landers and rovers all studying Mars over the past 6 decades. We know more about it than any other planet outside of Earth. A dusty, cold rock covered with a thin layer of carbon dioxide. It's far from Earth's warm climate and breathable air, but not far enough to stop humans from actually going there. And finally, in the 21st century, Mars is now within reach of humans. Within some of your lifetimes, we could see humans set foot on the red planet. But how will we actually survive the journey? And what will life look like when we get there? That's coming up on this episode of Moonshot. But first, a word from our sponsors.
Close to the Earth, we have the Moon. And beyond that, what do you have as a target for human exploration? Venus is a hell world, impossible to land on, and Jupiter's too far. Mercury is a boiling wasteland, so Mars it is.
This is Alan Duffy, an astronomer and associate professor at Swinburne University of Technology in Melbourne, Australia, and lead scientist of the Royal Institution of Australia.
We talk about Mars as a romantic destination. We've seen it in the night sky for our whole existence as a species. The god of war has always been there for us. The challenge is set. If you see it, you want to explore it. We've done the Moon. We can't do Venus, it's too hot. There's Mars, and that's why we're going to Mars.
When you look at all the different planets in our solar system, Mars is the closest habitable planet that we have, which makes it the best next target for human spaceflight. And there's an awful lot of attention on getting humans there within the next decade.
The Earth-Mars synchronization happens roughly every 2 years. So every 2 years there's an opportunity for to fly to Mars. So then in 2024, we want to try to fly 4 ships, 2 of which would be crewed, and 2 of which two cargo and two crew.
That's our favourite spaceman, Elon Musk. One of the many companies he runs is SpaceX, a company you probably know about from the time they launched a Tesla Roadster into space.
The second stage sent Elon Musk's Tesla Red Roadster into space, along with a spacesuit-wearing mannequin named Starman.
Back in February, Starman was launched aboard a Falcon Heavy rocket from Cape Canaveral, Florida. The mannequin is riding in the driver's seat, as you can see, of a Tesla Roadster wearing a fully functioning SpaceX suit. He looks cool, doesn't he? SpaceX says the trip will help test the suit and prepare the company for flights with human passengers.
The company does more than just launch cars into space. They launched satellites and are now approved to resupply the International Space Station. But the reason they sent Starman into space was to test everything that they need to actually send humans to Mars. And Elon's hoping to have humans there from around 2024. Here's him talking at South by Southwest in 2018.
I mean, the moon and Mars are often thought of as like, is this some escape hatch for rich people? But it won't be that at all. It's for the early people that go to Mars, it'll be far more dangerous. I mean, really, it kind of reads like Shackleton's ad for Antarctic explorers. You know, it's like difficult, dangerous, good chance you'll die. Excitement for those who survive. And I think there's not many people who actually want to go in the beginning, because all those things I said are true. But there'll be some who will, for whom the excitement of the frontier and exploration exceeds the concern of danger.
As Elon alluded to, actually getting to Mars is pretty dangerous. First, you need to get to space. And then you need to get your spaceship and then point it at Mars, and then you need to survive the journey to the planet. And then, because you'll be traveling at incredibly fast speeds, you need to somehow slow down your spacecraft to actually land on the planet. Then once you land, you need to somehow build everything you need to survive. And so we're going to go into a few of those steps. Rockets are currently the only means of launching objects into space. Huge chemically driven engines that launch objects out of Earth's atmosphere at tens of thousands of kilometers per hour. We've heard on Moonshot before that getting out of Earth's gravity well is pretty difficult, and any long-term space mission will require hundreds of tons of equipment and cargo. More weight means bigger rockets, and that's a big dilemma for any space mission.
So propulsion has changed dramatically since Apollo. What we now have in propulsion, we still have the curse of the rocket equation, right? Which is that to lift more weight to orbit, right, to escape the gravity, you need more fuel, but now you need more fuel for that fuel, and so it goes. So there's an exponential increase. So you really want to lift as little as you can.
Now, Alan Duffy says that one of the ways that you can solve for dealing with Earth's gravity well is to send many smaller rockets ferrying all of that cargo and goods into space and then load them onto a much bigger spaceship for the journey to Mars.
We're talking megatons of equipment, supplies, redundancy, failure, the actual craft itself, of course. Here's where propulsion has changed. Big rocket to get out of Earth, but once you're in space, you can use ion propulsion instead. So in other words, there's no friction, there's no air resistance. So a little bit of force, a tiny breath of wind, these ion propulsions are just a tremendously low impulse, but it's constant. And it just keeps building. So imperceptible in the beginning, but by the end you are going faster than any spacecraft has attempted before. And our ion propulsion technologies are far more fuel efficient and ultimately, I suspect, will be the design of choice to get us to Mars.
So once we can get ourselves off Earth and into space, actually sending our spacecraft with all of that equipment to Mars is relatively simple. But just because getting the spacecraft to Mars is simple, that doesn't mean sending humans there will be a breeze. The Apollo missions, which sent astronauts to the moon and back, lasted 1 to 2 weeks, and we have sent people to the International Space Station for more than a year. However, any missions to Mars will take months to travel each way, let alone the time spent on the surface, which means we need to completely reimagine space travel to even get there. And on a trip to Mars, we want to save as much space as possible. We know we can save fuel by using ion propulsion. But what about all the food and the water that we need, and all of that equipment? And what about some of the other issues in space that arise as we travel for months and months on end?
In general, radiation exposure is not a good thing. It does things to the human body that result in bad outcomes.
This is Dr. Jen Fogarty. She is the chief scientist at the NASA Human Research Program, which studies how humans can spend long periods of time in space. The study looks at everything from food and nutrition to radiation and the long-term effects of zero gravity.
I've learned so much more about space radiation to try to really wrap my brain around this hazard, because it is a very unique one, but that the design of the vehicle, the hull, is been informed, to protect the crew from solar particle events, to be honest. You're talking mainly gamma and X-ray.
One of the biggest risks in travelling beyond Earth is exposure to radiation. The Earth's magnetic field and atmosphere creates a shield that protects the planet from the worst radiation found in space. We know on Earth that radiation can cause all kinds of problems, and we can deal with those problems in space for astronauts on the International Space Station. And because the International Space Station is so close to Earth, if for some reason there's an issue with the shielding, we can always send supplies. But once you travel into deep space, out of reach from Earth, we need to take extra precautions to protect ourselves from all that radiation.
But you're really most vulnerable when you're during your transit. We're trying to understand acutely, like in mission, is there a radiation risk? Could you acquire damage to your brain via these tracks that are made that cause your behavior to change? That is really a radiation-driven risk, but not recognized as one. And, those are very theoretical questions that we're trying to answer here using animal models.
Any humans making the journey to Mars will be exposed to hundreds of times more radiation than any human on Earth. And because you're in space for such a long period of time, that radiation will build up over the journey.
The more traditional sense is like, well, eventually cancer will happen. We're experienced, accidents here on Earth or wars that have included radiation exposure. So we have some idea of how the human body is impacted, but the type of radiation in space is very different than the one we've created here, exists here on Earth. So we're also trying to understand that is it uniquely worse? Is it the same? Is it just equally bad but different? So we do a lot of work to characterize that exposure.
Radiation is a real challenge. We have the cosmic rays, so the background radiation of space from exploding stars, feeding black holes, accreting black holes, if you want to be technically accurate. Those high energy particles bombard us here on Earth about 1 per minute per square centimeter, so about a postage stamp size bit of you. So constant, essentially. And it gets orders of magnitude more when you leave the Earth. Our atmosphere protects us, our magnetic field protects us. When you're in space, so that journey to Mars, you're constantly being irradiated by this cosmic field, by the sun's high energy particles. So you're copying hundreds of times normal annual radiation dosage on your journey.
And that radiation shielding Alan mentioned is going to be a big factor in the design of long-distance spacecraft. The thought is that in addition to the shielding on the outside of the spacecraft, all the water needed for the journey would be stored in the outer edges of the craft and help improve the shield, because water is actually a really good form of preventing radiation. But it won't be the only form of shielding required. And then once we get to Mars, the radiation problems don't stop.
When you get to Mars itself, its atmosphere is too thin, and there's essentially no magnetic field to speak of. So you have, again, very little protection from those sources of radiation. That's a really uncomfortable place to be. Our bodies can repair certain amounts of damage, but sooner or later, you will have mutations, you will have cancers, you will have other issues as well, indeed, from the radiation sickness. But at least at those low levels, you are dramatically shortening a human lifespan. What we can do about that is limited. We bring water for the journey, for example, and we surround our spacecraft with the water tanks. Water is a wonderful shield against certain types of radiation. And since we need a lot of water for the journey, that's great. It doubles up as our shield.
The other design issue we need to think about is how to make these spacecraft comfortable. You're going to spend months and months transiting between planets, and you won't be able to just step outside to get some fresh air if you start feeling a bit claustrophobic.
So as you can imagine, the vehicle will be a certain size. That size, for all intents and purposes, will not change for the duration of the mission. However, someone's need to have privacy may change. Someone's need to, not be so close to their other crewmates for a period of time may change. So how do you accommodate those changing needs? Something you could tolerate earlier in the mission is not something you can tolerate later, but I can't affect the vehicle architecture later. So you have to get creative. This is where potentially things like artificial reality or virtual reality could play a significant role for us to give the illusion of change and stimulus.
And those artificial environments could be just one way of helping you deal with being away from your home, tricking your brain into believing that it's still somewhere else, and could be a very effective way of coping with the monotony of being in space. And Jen says these psychological issues can actually become really serious on a long-term mission.
the psychological duress is a very serious issue, and we actually have it in our nomenclature. It's like a red risk. It's one of our more looming, pressing issues that we would like to have a lot more characterization of and solutions that have basis in data, as opposed to you get a lot of stuff that's anecdotal, what people think made them feel better. Well, we'd actually like to quantify it because we're building and designing all of this for people who, when they travel to Mars, they might not be born yet, the crew of the future. So it has to have more general applicability.
Each person will need to be comfortable working in close quarters with all the other members of the crew. Think about seeing the same people every single day. Everyone on those missions will spend 24 hours a day together for the entire journey. The spacecraft will only be so big, as will the habitats that we need to build when we get there. So NASA is spending a lot of time on Earth experimenting with living in confined spaces to learn what is required when picking the team that will make that first voyage. And they've run a bunch of simulation experiments putting people in close proximity to see how they adapt. There's an experiment that runs in Hawaii called the High Seas Experiment, and there's a really great podcast on this called The Habitat. I encourage you to go and listen to that. But the makeup of that first crew will be incredibly important.
When you're picking a crew, there's groups of people who will work together better for various reasons. And there's a lot of work done on both leadership and followership. And you can imagine through a mission that's at least a 6-month transit, plus, as you pointed out, a stay on the surface, depending on what your goals are, could be as little as 30 days. And then your return would be about 6 months. But if you stay past that, you're going to be staying for a while, 12, 14 months. And then return in a 6 months. So now you're turning it in from a 1-year mission to a 3-year mission. There's no in between that's reasonable with respect to how technologically how we would accomplish it.
The trip to Mars will take at least 6 months each way. And adding in a mission to the surface, the whole journey would take at least a year, assuming that you don't spend much time there. Everything the mission needs has to be taken with you. And as you know, there's no infrastructure on Mars, there's no food, nowhere to live. The International Space Station is resupplied at least every few months. But that's not an option for those longer-term missions. This means a year or more's worth of food, water, air, and equipment needs to be designed to fit into the spacecraft.
It's a closed system. So for all intensive purposes, you're building an exoplanet, right? This thing has to contain everything these individuals need to not only live, but thrive, because the expectation is these people are capable of some pretty high functions, both cognitively and eventually physically. So how do you make sure we meet all of their nutrient requirements, caloric requirements, stimulus requirements? And then, of course, we make waste products. How do you recover these waste products and recycle? We are talking about living off the grid.
And yes, recycling means exactly what you'd think. We can't let any water go to waste on a mission to Mars, so every bit of urine you pass will be collected, and then it will be reprocessed so you can enjoy clean drinking water over and over again.
It's quite the extraordinary purification process. It does result in, a tertiary waste product that you say, well, okay, well, that one I really have to get rid of. You have the vacuum of space and you can eject things at times if you have a precipitant. But the idea is, you are at a level where you might need to be 95% plus recovery of water. We can only carry so much with us. You probably have propulsion systems that might synthesize or have the capability in some processing way to synthesize some water, but you really have no new resource. So your whole water balance has to be thought through for the whole mission and how you're going to manage that across the people and be mindful of how much fluid the people require to maintain their health.
And maintaining health on the journey is a pretty big deal. So we'll have more on that issue right after this break. Welcome back to Moonshot. I'm Christopher Lawson, and before the break, we were exploring some of the issues that humans will have to deal with when we take that first voyage on a spaceship to build our new home on Mars. And besides the issues with radiation and dealing with our waste, there's also the problem of health. We talked about the psychological problems of dealing with cabin fever, but there's another big issue for anybody taking a trip to space, and that's a change in gravity.
Being in a lower gravity environment is a really stressful situation for the body.
This is Scott Solomon, an associate teaching professor at Rice University and the author of Future Humans, Inside the Science of Our Continuing Evolution.
One of the examples of something that happens to the human body when it experiences microgravity or just a decrease in gravity is that without the compression that we normally get on our bodies, our muscles and also our bones start to weaken. And so this is why when astronauts come back from being in space, they often are actually physically unable to move, unable to walk on their own until they're able to build that muscle back up. And the bone strength takes even longer to recover.
In the case of low Earth orbit and during the transit, unless you provide another source of gravity, you're in microgravity or near zero G.
That's Jen Fogarty again. And NASA has done an awful lot of research on gravity and the effects on humans because we send so many people to the International Space Station. Gravity is something that we take for granted. Humans can live in Earth's gravity, it keeps us grounded, so to speak. And when you take that away, a lot of things in your body begin to change.
You think about, lifting your own body weight up and out of a chair or standing up and experiencing swollen feet at the end of the day. Those things don't happen because you don't have the pull of gravity. It also doesn't cause you to have to do a lot of work to move around, so life gets very easy.
If you're trying to build muscles and strength here on Earth, you need to spend plenty of time exercising. As soon as you stop training, your body stops building those muscles. The same thing happens without gravity. Your body has developed strong bones and muscles to handle living under the force of gravity. These allow you to walk around and move on a day-to-day basis. And as you move around, you're constantly keeping those muscles active. However, once you're weightless, your muscles and bones start to lose strength.
And your body no longer invests in things it doesn't need. So it's not going to lay a lot of bone density down if you don't load bone. It's going to reduce muscle mass because you don't need to push. There's no weight. There's some mass, but it's not weight. So large objects, heavy objects don't exist. They move, and they can move kind of quickly.
Astronauts on the International Space Station spend an average of 6 months in a microgravity environment. This means they float around in the station and they aren't experiencing the gravity that we're used to on Earth. But to counteract the effects of zero gravity, they force themselves to exercise, spending about 2 hours each day working on maintaining muscle tone and bone density.
But our countermeasure, our intervention has been to say, go do resistive exercise. Go put a harness on and we're going to strap you to a treadmill and we're going to have you run not at your total body weight, because that's a lot of pressure on your shoulders and your hips because we don't have a unified system where you're being pulled onto the treadmill, in a vertical column. And you say that gives us some impact loading. It allows you to have a cardiovascular. So your heart does have to do work. And we do that for, an hour to 2 hours a day.
Russian cosmonaut Valery Polyakov holds the record for the longest spaceflight, spending 437 days aboard the Russian Mir space station. When he landed on the 22nd of March 1995, instead of being carried out of the capsule, he insisted on walking the short distance to a chair to prove that humans could be capable of walking after such a long period of microgravity.
When you talk about the lack of gravity and, again, how the body will change and adapt and you have less muscle, skeletal muscle, we've studied the heart quite a bit to understand the changes in the heart, and your heart does adapt. In none of those cases have we seen someone cross a threshold that made them incapable of functioning on Earth, but the transition can be pretty rough. So your first 24 hours being re-exposed to gravity after a long duration spaceflight, your body can really struggle to figure out how to be responsive to gravity again. and kind of recalibrate its function. Because a lot of your body systems are dependent on sensors, biochemical, electrochemical. And what's interesting about those sensors in your body is that when you went into space flight, when an individual goes into space flight, a lot of those sensors, because of the lack of signal, lack of gravity, have turned up the gain super high because they're looking for signal. They just can't find it. And over a while, like that, the sensors habituate and kind of they're like, okay, well, now we're going to let it go, and then you get tissue adaptation, like all the right things start to occur from a biological process standpoint. You just say, but the body doesn't realize that you're going to go back to gravity. So don't totally remodel.
When astronauts return to Earth after a long space mission, they undergo extensive medical testing and sometimes rehab to ensure that they completely recover from their mission. And there's many people there to collect them. But when humans go to Mars, there'll be nobody on the ground to meet them, at least initially. Any humans going to Mars will have to help themselves out of the landing craft and onto the Martian surface. And Alan Duffy says the first step on Mars might not be as glamorous as the first step on the Moon.
The challenge is immense. We talk about travel times of half a year to 9 months. That means you're exposed to radiation along the way. You have natural body wastage. You have all the challenges of microgravity. Our astronauts in the space station, essentially need to be helped the moment they return to Earth. So it's not going to be such a heroic first step when you come off the spacecraft on Mars and you collapse and you break a knee. I mean, there's a very real possibility they'll do their hip rather than take a heroic first step.
So once we get to Mars, how do we actually live there? We'll hear more about how we go about sustaining life on the Red Planet in the next episode of Moonshot. This episode of Moonshot was hosted by me, Christopher Lawson, with assistant production from Patrick Laverick. Breakmaster Cylinder composed our theme music, and our artwork is by Andrew Millist. Make sure you subscribe to the show so you can hear part 2 of our episode looking at the Mars missions. And if you appreciated the work that went into this episode, share it with at least one friend. It really helps. And if you're feeling super generous, you can also help us out with a donation. Visit moonshot.audio/donate. We'll see you next time.